excited to be here. Chaos Personalized Medicine WEP event 2020. A lot of exciting science, positive energy, and I encourage everyone to join us.
Hello, I'm Jeff Shama. I'm a professor of electrical engineering and the director of the Center of Excellence for Neome Research at KAUST. I'd like to welcome everyone, welcome the KAUST community, students, staff, faculty, and special visitors from the kingdom. Welcome to KAUST and welcome to this WEP keynote event. I'm very pleased today to introduce Professor Chih-Ming Ho. Professor Chih-Ming received his PhD from Johns Hopkins University, and he's had a long and distinguished career at UCLA, where he held a Ben Rich Lockheed Martin professorship until his retirement in 2016, where he is now a distinguished professor emeritus with UCLA. Indeed, I had the good fortune to collaborate with UCLA with Professor Chih-Ming while I was at UCLA, and we even had a couple of joint papers together. So I had the good fortune to have him as a colleague. His research spans many areas depending on which part of his career you're looking at. And of course, we're going to hear about phenotypic personalized medicine today, but he also has had distinguished contributions in micro and nanofluidics, molecular sensors, and analysis and control of turbulence. Among his many, many accolades, he's a member of the U.S. National Academy of Engineering and an academician of Academia Sinica. He's received an honorary doctorate from Hong Kong University of Science and Technology, and he holds 10 honorary professorships globally, including the Einstein Professor from the Chinese Academy of Sciences. And finally, he is ranked by ISI as one of the top 250 most cited researchers across the breadth of engineering. It's really a great pleasure to have him here for this WEP event, so please join me in welcoming Professor Chih-Ming Ho.
Thank you. Thank you very much. Especially thank you to invite me to KAUST. That's my first time to visit KAUST, and I was really impressed by the people and also by the facility and by such a nice environment for all the people can stay here to do research and learning. Okay, today I'm going to talk about the disease is a personalized matter. I think everybody will agree when we get sick, and it's really horrible for us, and also it's different from everybody else because we suffer that. Okay. Before I start, I want to really acknowledge my student, the group of the students. I have 50 PhD students. They are really fantastic. All the work we did and we talked about and all from them. They are smart. A lot of the students, I even didn't tell them what is your PhD thesis. They tell me what will be his PhD or her PhD thesis, and the work they did is fantastic. A lot of visitors, and also I work with maybe 30, 40 different laboratories around the world. And that was a quite interesting experience. Okay, so personalized medicine. Sir Osler made a statement 100 years ago. Medicine is a science of uncertainty and an art of Who's Sir Osler? He is the he's the father of modern medicine. He's one of the giants in the modern medicine. But he made a statement like that. I think for us, for a patient or for a doctor, really doesn't feel that's not good enough. We cannot, our life cannot be just a probability and, or uncertainty. 100 years later doesn't make the difference, okay? And it's still, the medicine is a science of uncertainty and an art of probability. During this 100 years, many, many advancements have been made, both in diagnosis and also in therapeutics. And why still rely on the probability? Because so far, all our new drug development, our sensor development, is all based on population average statistics. We always, like a new drug, phase 2, phase 3, we get thousands of patients. We test on that and say how many % of the patient will be beneficial by the drug or how many of them are not. We can never say how can we develop a drug will be good for everybody. We don't have that technology. So everything is based on population average drug and a dose, not based on personalized. We do not know how to do it, but now we know how to do it. That's what I will introduce in this talk. And this talk, we actually dealing with one of the most complicated phenomena in the nature. How do we make sick people back to health again? But I guarantee you will be able to understand it because disease related to biology, and we need some math to do it. First, I don't understand, I don't know anything of biology. I was trained as an aerodynamist. And for math, I only know how to add and subtract. So that's all we need in the whole development of this personalized medicine. So definitely you will be able to understand everything, what I'm saying. Okay, so based on population average statistics, this is the result. We based on the population average the chemotherapy. 1 out of 4 patients has response. For example, breast cancer, 25 to 50% of the patient has response. Doesn't mean they are cured. Okay, their response to the drug has positive response, and 75% they don't. They just have to suffer this chemo. And for some cancers, pancreatic cancer is 15 to 25%, liver cancer even lower. So that's at the current, what is the chemotherapy can do for a patient. And all of that is still based on a percentage. So let me show you one example. That's what we did in our lab about in the last year or two. So what we do is we take a rat model. This rat is not a wild type of rat. It means all these rats come from the same family. So genetics is pretty homogeneous. And we work on the colon cancer. The colon cancer, we use a cell line. It's not a PDX line. So the cell line is also genetic homogeneous. So we use genetic homogeneous cancer cell line, put on the genetic homogeneous rat, and then we use 4 drugs to treat. These 4 drugs to treat the rat. So from day 1 to day 13, just like we treat all the cancer patients, we use the same dosage, quarter and of MTD of the 4 drugs. So what is MTD? It's the maximum tolerated dose. If you give higher than the MTD, the rat or the patient cannot accept that, will have toxicity. So what we do is the 4 drugs, we take a quarter of MTD to treat these 5 rats. You see every rat behave very differently. So from day 9 to day 13, the growth of these tumors, they are pretty much a straight line. So we plot the growth rate for rat 1, 2, 3, 4, 5, 6. These 5 rats are all treated. One rat is pretty good. The tumor doesn't grow anymore. Another rat is pretty bad. Even they are treated, the growth rate is the same as the one who is not treated at all. And it's 1 out of 5 rat has response, and all the rest of the spreading around in the between the treated and the best rat. So that's from the day 13, the day 0 to day 13, and they are treated with the same dose. I will tell you later what happened after day 13. So why we have these problems? And this problem is from the beginning of the medicine, maybe 5, 6, 7,000 years ago. And until now, and still a problem we cannot answer. So we give a patient a drug and a dose, then we hope the patient has the efficacy, okay? So getting better or getting worse. And what we do is we do testing. We put this drug dose to the patient, and sometime later we measure getting better or getting worse. What we really would like to have and have quantitative governing laws. If we have a rule, can relate input and output, and then that's not a problem anymore. I can say, I give this dose to the patient for a kind of response. If I have the rule, I can take a differentiation, I can optimize what is the best dose for that patient at that moment. We don't have it. So why we don't have it? The fundamental challenge, a drug or the molecule, the size of the drug molecule is in the nanometers. A disease is a system problem, okay? Cancer in the liver, yes, cancer in the liver, but the whole body system becomes sick. So the system problem is about 1 meter. So the 2-length scale, one is 1 nanometer, one is 1 meter, is 9 order of magnitude apart. So anything what we learned in the small scales doesn't work at the meter scales. And in addition, it's not homogeneous of the system. We start with the molecules, and then we form the fundamental, we form the fundamental system, which is cell. Then the cell-cell interact, and the form a tissue, then form organ interact until become the body. And we know a lot about the molecular mechanisms inside the cell. We really don't know very much at all the mechanisms between the interactions at this stage, and that stage. However, our life, we can live on average 85 years old. And sometimes we're getting sick, but we have a pretty robust system, and we can go over that disease and we can live pretty well. So there must be a governing law. There's no way all the molecules, all the cells in our body just going around randomly, and we can live that long, has a reasonable good life. So there must be a governing law. So what is a global governing law? That's the question we are asking. Okay, so we take a drug, and the drug get into the body, going through the liver, and eventually go to attack the diseased part of the organ. And big data, yes, it's indeed big data, because when the drug get into the body and going through livers, going through all the organs, eventually try to attack the sick disease, and all these chemical reactions and physical reactions and also the organ reactions is really a big data. So dose and the dose, drug and the dose go through this process, finally show up the phenotype, getting better or getting worse. Okay, we don't know. We don't know this big data part. However, in the clinical medicine, the doctor treats a patient, he has only 2 parameters he can change. He can change the drug and the dose. Okay. On top of that, if you want to get one more data from the patient, and that costs a lot of the patient's health and even life. So we do not have that many data we can collect. However, we should be able to treat the patient and improve their health. So that's a problem. That's a challenge. So how do we treat the patient? Nowadays, in any disease, we always treat the patient with combinatory drug. We do not treat with one drug. We treat with several drugs. In Chinese herbal medicine, we know that a few thousand years ago, and we always treat a combinatory drug. And the Western medicine always treat with one drug until 1995. The HIV started recognized being a disease, a deadly disease in 1980s. The death rate kept increasing linearly. Until 1995, 3-drug combination was developed. So the 3-drug combination in 2 years, the death rate dropped 66% and keep dropping. So the combinatory drug is really powerful, be able to handle something which is very hard to handle with. I have 2 controllers. I have to decide which one is the one I need to push. So nowadays, combination drug is used by the doctors to treat almost all disease. But the combinatory drug was never optimized. How do you decide the dose? By phase 2, phase 3 test. Okay? And most time, the dose is very high because always people think a high dose has high efficacy, so people high dose and end up with high toxicity. So if you treat the cancer patient, always suffer very, very high toxicity. Why we cannot optimize that? N dosing with M drugs is N to the nth power. 6 drugs with 10 doses is 1 million possibilities. How can you test 1 million possibilities to find the optimum? So we don't. So we did take many people try out and take the average. Okay, drug. We developed a drug. You know how much time and money to spend for the drug? A new drug takes 10 to 15 years to develop and takes $2 to $8 billion. And the successful rate from animal test to phase 3, end of phase 3 is 1%. Okay? So not that easy to get a new drug and very expensive. So when we develop all these new drugs, now we mostly based on omics, based on all the molecular mechanisms from DNA all the way to the protein to the metabolomics. And it's so complicated. You can find hundreds, thousands of papers in Science, Nature, in all these biologies. And it really doesn't help very much. Few of them does find out which drug or what is the mechanism really will cause that disease. Okay. And another thing is we talk about the landscape separated so far. So we really talk about a very, very big database. And a lot of things we do not know. But then we have to find a way to treat the patient. So we have to do something which is different from what we did for the last 50 years or 70 years. So that's what we start with, want to find something to do it. As I said, I don't know anything about all this biology. The way I started working on this area was once I was discussing with one of my good friends. She is a very famous biology. So I said, teach me biology. My biology was 50 years old. During that time, even DNA was taught in my textbook. So she started to talk about build up all these molecular mechanisms, and as a cell, as a computer CPU, want to build all the circuitry. I said, no, come on, I cannot. I'm too old to learn. But there must be some other way. And we argued for a whole afternoon, and then finally she left. And then I get one of my very smart students. Said, let's try use a feedback concept. We use all the time in engineering. We try one. If it doesn't work, we use a game theory to guide us to do another one. Okay? So in 1 month, we got it. So something which doesn't work and spend so much money, so much time, that means something wrong, and is there any other way can do it? So we have to come out with an orthodox approach and come out with disrupt technology. It's not just say, I wanted to come disrupt technology. We have to have a guidance, have a pathway to reach that point. Usually the point happens at the interdisciplinary area. Engineering, biology happens between the two fingers at the interface area. Okay? If you can really put these two fields or three fields together, right, and you will be able to find it. That happens not only in the medicine development, and it happens in everything. So we need to integrate engineering, medicine, and science to discover, to invent for enriching human life. It's art. It's not a technology. Technology or science, there's a rule you can follow, you follow to doing that. But if you want to put these three fields together and find something really disruptive technology, it's very much like a chef. Use the ingredient. And the best chef, he can cook something out, everybody tastes really good. Okay? And that's art. So how do you put all this together, integrate, and finally the come out result is very exciting to fit our purpose. Even that, most important thing is enrich our life. We cannot just doing something and write a paper in science and we'll be happy about it. We get all the research funding from taxpayers' money. We have to return. We have to help them and also help us, especially in this field. Okay, so the choice, the one we took from the engineering part is artificial intelligence. The artificial intelligence, how the one part of that, one way to do that is it can relate input and output with a quantitative relation. So they can integrate, they can relate drug and dose to efficacy with a quantitative relation. And most importantly, mechanism-free. We don't have to know what inside. And that's very good for me. I don't understand biology. So use this method, I may be able to find a way to link input and output, and maybe we'll find a way, try to do, find a good way, try to do treatment, disease treatment, and even to the personalized treatment. Okay? So what is the AI? AI, many things, can do many things. The AI we will use is a very rudimentary part of the AI. Basically, we use a lot of data to train the AI algorithm. What do we want out? Find out the landscape of the efficacy and the drug dose. Okay, I want to find how does the responses surface of the body to the drug dose variation. And the base is a smart curve fitting, that's all. And because this mechanism free, so indication agnostic, if that works, I can use the same thing to treat all kind of disease. And this finally, so the first author actually was a postdoc by Sharma, Professor Sharma. He's a very smart applied mathematician. So he used a neural network, a very simple neural network. Then we have hundreds of cell line test results to train the neural network, and I want to find out the drug dose response surface. So he come back in a few weeks. He showed me the result, which is really surprising. I couldn't believe that. So what we did, we take the HSV1 viral infection, which is a herpes virus infection. We take 6 drugs, and about 600 experimental data, experimental results. Each result is about 100 of data. So it's a large amount of data to train the neural network, and finally the curve shows efficacy of killing this infected cell. Drug dose 1, drug dose 2, a smooth surface. Drug dose 3, drug dose 4, a smooth surface. How can that be? The drug gets into the body, going through all these organs, and finally try to find out the infected herpes cell and kill it. And it's a smooth surface. So in other words, the plot shown many times during the talk, input and output related by a phenotypic response surface. That's simple, a smooth surface. But we use 500 to 600 training experiments, about hundreds of thousands of data points. We got a very interesting, very simple, smooth surface. That's not good enough. Why not good enough? Because we need so much data to find this surface. Okay, still too many data points we can afford. So I have to find something else. The reason for that, clinical medicine, small data, a few data points. So how we do that? So I say, hey, such a smooth surface, you must be able to find out the equation to fit the surface. That's how it come back. What is this equation? C is the dose of the drug. CI squared is the dose of the drug to second power. CICJ is drug-drug interaction. It's an algebraic equation. If two drugs, it's such a simple equation. C1 plus C2, C1 squared plus C2, and C1, C2. So that one describes the whole thing, the drug getting into the patient, and how does the patient will respond by efficacy or by toxicity. That's it. Why we are so excited to get such a simple equation? Because this equation enables us to really start to do personalized medicine. If we don't have this equation, n dose for each m drug is n to the mth power. That's huge. 6 drugs, 10 dose, it's a small, 2 small numbers become 1 million possibilities. We have this equation. We just need to do a small number of tests to solve the coefficients, xi, yii, jij. Okay, it's a small number. How small the number is? If 3 drugs, usually when we do treat patients, 3 or 4 drugs, 3 drugs has 10 coefficients, so we do 10 tests, and I can solve the equation, I can optimize. But if you use the n to the m, if each drug has 5 doses, it's 125 experiments. If 4 drugs and has 15 coefficients, it will be 600 tests. We did an experiment for Gates Foundation, trying to find out the new drug combination for TB. So we start with 14 drugs. 5 doses each drug is 6 billion possibilities. Or I have to do 120 experiments. I can find out the best drug dose for treating TB. A very simple math. It's algebra. Okay? And usually when we do the in vivo test, like for clinical test, animal test, we only treat patients with 3 or 4 drugs, so a small number of tests. We will get the best optimized dose. If we do that on a patient, that's a personalized medicine. Okay, so we talk about for cancer. Cancer is still a very difficult the disease to treat because the response rate is very low. 1 out of 4 patients has a good response, and even that survival time is very short. So why is that? People attribute it to 2 reasons. One is omics, genetics, and all this molecular mechanism, and another is physiology. Physiology, everybody is different. Even identical twin, the physiology of these twins are different, okay, because of these problems. Then we say, okay, now let's do the animal test, which cannot be done in the human. So as I said, we use a genetic homogeneous rat, genetic homogeneous cell line, and we find out how does a combinatory drug treat these 5 rats. Day 0 to day 13, you have seen that all the 5 rats behave very differently. So from the treatment and the tumor growth with our method, from day 0 to day 13, I can find the optimized dose for each of the rat. So after day 13, I don't treat the rat with the quarter MTD. I treat the rat with the optimized dose for each of the rat. So from day 1 to day 13, we show that results. The treat with the same dose, and the fourth rat is very good, fifth rat is very bad. Okay, remember that these two rats, one is very good, one is very bad. After day 13, I know what is the best dose for each rat, and I will treat this rat. Look, IR04, the dose, normalized quarter MTD is 1, 1.2, 1.23. Rat 5 is 0.2, 0.2, 1.2, which are complete opposite. Okay? Then, after I treat each rat with different dose combination, you see how does the rat respond. Everyone get a very good response. Very simple. Okay? We treat the rat with a certain dose and measure the tumor growth for calibrate 13 days, and we can make every rat behave very good. That equation is an algebraic equation. Even I can solve it. You must be able to do it. You know, I always joke, in my laboratory, the best student produce the best is undergraduate, then graduate, then postdoc, become professor, become useless. So if a professor can do it, everybody can do it. Okay, so next experiment. This is a clinical test. For all this kind of medicine study, if you cannot bring to the test on a human, and nobody will believe that, because a human has the most complicated physiology. So this patient is an 85-year-old patient, has prostate cancer, metastatic. That means his prostate already removed, but the cancer get into his head bone, has a 6-centimeter lesion there. Okay, and they use two drugs. One is the ZN3694, and another one is enzalutamide. Enzalutamide is a drug on the market. Zen is a new drug. This experiment was done at the UCLA Medical School. Okay, he started with the PSA. PSA indicates how bad is the cancer. He started with 30. Normal range is below 4. So the patient, and the doctor, Alan, he treated this patient for about more than a year already. And the dose ranges from 36 to 48 milligrams. And so, but the toxicity is so high, so the patient cannot survive, cannot stand. And then, actually, this new drug test, we have about 30, they have about 35 patients. All the 34 drop out because of toxicity. And this one is a really strong person. He worked for more than a year, and then he said he will drop out. Then we take the data from the doctor's treatment. We plot that. It's a beautiful parabolic surface. Okay, so that's true. We didn't conduct the experiment, and it's done by the doctor, and we measure the results. So it's a parabolic surface. So after we get a parabolic surface, we tell the doctor, you drop the dose. Drop to 24. Doctor say no. Usually doctor doesn't want to change the dose. If you want to decrease the dose, they always think that efficacy will drop. We said, no, it will not. So he said he cannot do it. So the patient said, I will drop out. If drop out, the new drug is out. Okay, so then the doctor go back to talk to the company talk to FDA. Finally, they let us do below 36. We did for below 6, and that's the red points, and the PSA dropped to 0.64. So the doctor is pretty happy. The patient is very happy because he can stand the toxicity, but still suffers some of the toxicity. So he said, how about a drop to 12 milligrams? No. We told him, if you drop to 12 milligrams, based on his PRS, we know that your PSA will increase, but he insists. So 2 weeks after drop to 12 milligrams, PSA goes to 1. Another 2 weeks go to 1.56. Another one go to 2.0. So then he go back to 24. Okay. So such a simple equation and really can get the the patient responds so well. But one thing is very dynamic. Even you don't see on this graph, if every time we get the new measurements that we put into the equation, and the parabolic surface will change. So we always use a new parabolic surface to predict the next one. So that's cancer. For HIV, is a infectious disease. So how do we treat this kind of disease? At the day 0, the patient come in, usually has very high viral loads. So the doctor will find out a drug combination usually with a high dose, which is approved by FDA, and treat the patient. In few months, the viral load will drop several orders of magnitude. Will go down to the detection limit, which is 40 copies of HIV virus per cubic centimeter of blood. How the patient is treated? They still treated at the day 0 with very, very high dose. Okay? So what will happen? And the toxicity can be very high. In this drug, TDF is a drug that has long-term toxicity. After a few years, the kidney will be damaged. A patient dies of kidney failure. Or the calcium will lose from the bone. So the bone can be easily cracked. So what we want to do is we want to try to reduce TDF. The drug reduction happens in all the combination drugs. And especially for the patient has to take a long time, take a lifetime. So based on our equation, which is a parabolic equation, in one drug is a parabola. So these are the 10 patients parabola. You can see the lowest dose for patient 6, he only needs 120 milligrams, not 300 milligrams. The highest one, he needs 260 milligrams. So in the range more than factor of 2. So you can see every patient is different. If you treat this patient at 120 milligrams, he will not, in long term, he will not suffer all these toxicities or side effects. So disease is personal. Treatment has to be personal. Okay? And with this equation, it makes everything become possible. Organ transplant. So we did many, many disease models. I just show you 3 major disease problems: cancer, infectious disease, and organ transplant. Turns out the organ transplant is the most difficult one because it's very dynamic. So we have to change the dose every day. Top one is a control patient. That's a doctor's patient. So you can see this is the input drug. That's the marker. They want to keep the marker within this white shadow region. This drug is a neurotoxin. You have to keep high enough such that it will suppress immune system, no rejection. But too high, the patient will behave differently, have seizures, or speak like a crazy person, or cannot respond to the orders from the nurse or from the doctor. Too low, the drug will, then the organ will be rejected. How low or how high it is? It's 2 nanogram per ml, a very, very narrow region. So the doctors usually do titration, too high, then drop the dose, then become too low and gradually to increase the dose. Takes a long time to go into the range, and the next day maybe go out of range again. That's our patient. So use that equation. We did 4 calibration. We varied the dose. We did 4 variations, then we solved the equation. We know the coefficient, then the 5th point, 6th point, and we can do it very, very well. Okay? So we have the global governing law of the body's physical response. And we can solve that equation, and we can find the best dose. So that's what we did in the past about 10 years. We did about 20 different types of disease. Okay? And for the last few years, we moved toward the clinical test. We made 4 clinical tests, and we have 80 patients finished. The most proud result is 0 misses, not a 25% response rate. All the treated patients we did, everyone responds very well. Now we have another 7 ongoing clinical tests, another 400 patients going on. So that's a really quite exciting experience for our group, for me, because we can use a very simple equation, a very simple engineering approach, and can treat the patient with such great results. Simplicity and complexity. We talk about the human body response to the drug, getting disease and response drug. It's really a complex process. Okay? For example, molecule-molecule interaction and form the cell. Okay? In this scale, we know a lot about the molecule-molecule interactions. When you go to cell, interact each other, form a tissue. We don't know the mechanism. We see the phenomena. When you organ transplant until form the body, organ and organ transplant has a lot of interactions, especially when the drug get into the body. Okay? And all of that can be done by such a simple equation. There must be a reason. Okay? It's not a miracle. There must be a reason for that. So what is the science base? Why? So the science base is a field of science called a complex system. There are 2 issues, 2 volumes of science published in the last 2 decades. The whole volume talks about a complex system. So what is a complex system? Complex system has to follow 4 rules. 1, they have a lot of interacting elements. 2, and they interact self-organized. So they put it together. It's not engineered, so we put the parts together, become a 747. They self-organize. After they self-organize, has emerging property. Like if you open up my skin cell and open up my cancer cell, open up the inside the protein and medicine is not that much difference. But when they organize together, become skin cell and liver cell, they're all very different. So these kind of emerging properties cannot be predicted from a small part of the internal mechanisms. The 4th part, after long evolution, they are adaptive and robust. So pretty stable. We can live up to 80-some years. Okay? So these are the 4 fundamental mechanisms. What does that have anything to do with our equation? So our equation, efficacy related by that equation, okay, on this side. So what is the other side? Other side, C, is the drug molecules. They interact with all the different things inside the body, the cells, the organ, etc., that represented by this coefficient. So that one is the drug interact with a protein, for example. Okay? The drug molecule interact with a disease element. And the drug also, because of that, affect all the organs, etc. So that's the interacting elements showed by the red square. The other part is emerging property. After I did that, the patient become better or become worse. Okay? So really, this equation relates emerging property to the building blocks by such a simple equation. And with this equation, we can reach to the personalized medicine. So AI parabolic response surface, basically from input-output of the patient, due to the stimulation of the drug, we have an equation, we have a smooth surface. So we are all parabolas. I'm a parabola, you are a parabola. Your parabola is different from my parabola. My parabola tomorrow will be different to today's parabola. If we know how to get it, control that, and we will help a lot for our health and even our life. So don't think about life is too complicated, okay? Life can be very simple as a second-order algebraic equation, okay? And by doing this, and we can really realize a true personalized medicine. This is my website. So I have all this and all the paper we publish. So you're welcome to visit our website. Let me ask, from all our work, we mention about the genetics. We never dig into the genetics. Does genetics really is useless? No, it's not. There are play an important location. Let me show you. Does gene matters? Yes, gene matters. The other three pictures, my granddaughter, 6 years old. This one is my mother, 70 years ago. Now she's 102 years old. Look at them. They are 4 generations apart. They're almost identical. This must from genetics. So, but on the other hand, if we treat the patient, we use that equation. We don't look into that side of the story. Where is it? Where is it? That all in the coefficients. So we lump all the things we don't know into that coefficient. We calibrate the coefficients and then end up with, we can really treat individual patient of almost any disease. Thank you.
So thank you, Professor. We now have an opportunity for a few questions. Okay, we got it.
Hi. Thank you. Thank you very much for your talk. My question is, so if I get you correctly, each of us has a different parabola, which is a function of time and concentration of the drug.
Where are you? I couldn't see you.
Here.
Ah, I see.
Yep. So each of us has a different parabola, which is dependent on time and the concentration of drugs. My question is directed towards the method. How do you determine the parabola of each person?
Okay. So what we do is like you remember the organ transplant. In the first few days, or like in a rat experiment, the first few days, we have a way to change the dose. Okay? If we have 3 drugs, we change the 3 drugs in a way and follow a certain mathematical method and the experimental design. So we change the drug for a few days or for a few weeks, and then we measure the output affected caused by that drug dose. So after a few days, the changes and which match the number of equations. So we can solve the coefficients. After we solve the coefficient, we differentiate and then we get the results. Then we can go back to find what is the optimal dose for that patient at that day.
I see. So there is like a testing phase and then afterwards like a validation phase.
Yes, it's like a calibration. We calibrate the patient by changing the dose a few times. Okay.
How many times do you need to calibrate? Like how many
How many times?
points?
Depends on how many drugs. 1 drug, we need 3 calibration points. 2 drugs, we need 6 calibration points. But if you keep 1 drug constant dose, then it becomes 3. You do 3 times. So you can reduce the number of calibration because we like to calibrate that in a very short time so we can give the real optimized dose. Okay.
Okay, I see. Thank you very much.
You're welcome. Yes? Oh, sorry. Okay. Who's the next one?
Me? Okay. Yeah. Okay. Thank you very much for your impressive talk. I wanted to ask if there would be any benefit of considering higher polynomials for your objective function, especially if you have like multiple drugs. Like, have you considered taking, for example, a 3-order polynomial or 4th order, and considering like multiple local minima?
Okay, that's a question almost every mathematician or the one who knows math will ask the question. No, it's not. Because we cannot afford to do too many data points. If you go to 3rd-order polynomial, and then you have to do a lot more number of tests. Okay, that's the first thing. And from all our 30, 40 different experiments, the 3rd-order term doesn't mean it's not there, but it's positive, and the negative. If you add it together, 3rd-order, 4th-order term is almost 0, even in the noise level. So there's no reason we go to the 3rd level, okay. 3rd order of polynomials.
Okay, thank you.
Okay. Yes? Oh. Oh, Jeff, say how good you are.
Thank you very much. For me personally, I think it's one of the best lectures that I've heard. So I really enjoyed your approach with this equation and how this equation already saved few lives and it will save many more. I have a question regarding the different type of drugs. They may interact differently, and there is for sure some counter interactions that two drugs cannot be applied for the same person. How this equation can adjust to this kind of discrepancies between taking the different drugs?
Okay, that's a very interesting question. And okay, we have one experiment doing in the NUS, National Singapore University. We work with the Associate Dean of Medical School. He is one of the top authority on multiple myeloma in the world. Multiple myeloma is older people, men or women's cancer, okay? And it will produce an M protein, which will damage the kidney and then the patient die. So they use 3 drugs to treat the patient. So before any clinical test started, prospective, we always ask for retrospective data. So he sent us 8 patient data. 7 cured, 1 passed away. So we're going through this analysis. We can make that 3 patient with our method, 7 patients with that method. We can get treated during about 1.5 or 2 months, and the patient will be cured by by the drug and this method. 1 patient died. And we look into and analyze the data. We found that 3 drugs, 2 of them are antagonistic. Okay, so that patient treated by these 3 drugs for 1 year, and the M-band protein keep very high level and then drop to 0. The patient passed away. And this coefficient depends on person, depends on the dose, depends on many things. So we change the dose. We change the dose, we find out at a certain dose ratio, the 2 drugs become synergetic. So we can treat that patient in 2 months, and the M-band go to 0. And if we treat that, and the patient will not die. So the simple equation, but the coefficient is really the way you can play with that, and the dose you can play with that, and you can find out some really, really very good results. Yes, there's one person here.
Yes, thank you very much for the talk. Again, so I'm kind of going back to the slide where you talk about don't make it complex, but at the same time, do you see these kind of technologies getting across into clinical applications? Even though, I mean, if something happens, we don't know the mechanism that's responsible for this problem. We have a system that solved, the proper dose, but we don't understand exactly what's happening inside the body that made it work, that made it not work, and so on.
Yes, it will take forever to know why it works, why it doesn't work, especially like in organ transplant, it changes every day, okay? And for if you want to sort why the coefficient change, and that is really, really, it's not such a simple way. You cannot solve that part of the answer within 1 day time, okay? And okay, even you understand what is mechanism, it doesn't mean the same mechanism in another patient will give the same response. For example, like we change the patient, especially organ transplant, because we suppress the immune system, so the patient gets infected every day, any different things. So, like infected by bacteria, we give antibiotics, and the dose, the tacrolimus range will change. For this patient, we give the antibiotics for 50 milligrams today. So we increase the dose, increase the tacrolimus, and after 20 days later, and infected again, we give the same 50 milligram, and maybe we'll drop the tacrolimus dose. So human body is such a complex, the balance point change all the time. Okay.
We had a question here in the front. Can you pass the mic here?
So this one in the back.
Thank you, Professor.
We'll take this one and then go to the back.
Thank you for your presentation. You have shown good data about these chemotherapeutic agents. And as we know, like chemotherapy is not specific. It has a lot of side effects and toxic effects. So have you tried a combination of chemotherapeutic agent along with some gene medicine, something like siRNA?
Yes, we did. We did. We changed, like we use 1 or 2 targeted drug to treat the liver transplant. No, sorry, the liver cancer. And usually targeted drug, the advantage of targeted drug is the toxicity is lower, okay? But it's one target. But the problem is when a cell becomes diseased, it's not one pathway is wrong. Usually several pathways wrong, okay? Of course, we can use two targeted drug, and most of the time, even so far, no one used one single targeted drug. When you use single drug, they always use a chemo, because chemo can kill some other pathways, kill some other target. But on the other hand, toxicity is very high.
Because they can kill even the non-target cells also.
Yeah, sure, it is.
So that's why actually, like, to be specific, like for example, like a co-delivery of a chemotherapeutic agents along with some DNA delivery or a gene medicine, that will probably have like a very specific effect, and we can selectively target those particular group of cancer cells.
Yes, and if you know what are the other 2 or 3, usually when take a cell, okay, a cell when he get a disease, it's not one target, it's not 2 targets, usually 3 to 4 targets, but you don't know which other 3 or 4 are relevant to each other, okay? And we did the test. We found out what are the 3 targets, and we use 3 drugs to working on that. And yes, we can get good results, but at the same time, and still the toxicity is there because this targeted drug also will kill some other, and will still infect the other part of the pathways.
Thank you.
So especially in cancer, the toxicity is one of the most difficult things. Okay.
Last question here.
Thank you for your very fascinating talk. I'm here.
The back corner.
Thank you for your very fascinating talk.
Sure.
Just a few quick questions. First of all, in your slides about prostate cancer and how you sort of calibrated a treatment, you spoke about a phenotype, which was in that case a biomarker, the PSA. How would your equation play out if there are multiple phenotypes, for example, multiple biomarkers or sort of imaging, radiology results? That's the first question. The second
We can only take one question, so that's it. Okay.
We answer one by one. First, answer your question, okay? Suppose there's no such one marker can cure the disease. Usually, you need a few markers. Okay, so what we do is when we do the calibration, we measure all the markers, and after calibration, also we measure all the markers. So based on the drug variations and that marker, we can find the optimized dose for that marker. So if we have 5 markers, I can find the optimized doses for 5 markers. Most time, these five optimized combination drug, they are not at the same location. So you have to make the choice, okay? Which one is most important? Or if you're lucky, 2 or 3 of them clustered together, then you pick up a dose combination to make that few markers better for that few markers. Okay, it's not possible to make every marker have optimized dose which you can operate. You have a second one, or you
no, that's it. We're out of time. Thank you very much, Professor Chih-Ming. We have a gift for you.
Thank you. Thank you. Oh, thank you.
Thank you all for your participation.